Swayam Prabha. Digital India. Educated India.
We will now be continuing the discussion on the Benard-Marangoni instability that we had started in the previous lectures. Now, the linearized equations for the vertical component of the perturbation, that is W hat, and the temperature perturbation theta hat are shown as equations 12 and 13 on your screen. The domain is also shown in terms of non-dimensional variables x, y, and z, where x and y are the horizontal coordinates, and these are the x and y plane is parallel to the bottom surface, and x and y also go from minus infinity to plus infinity. But in the vertical direction, the non-dimensional variable z goes from 0 to 1. Now also notice that the equations 12 and 13, they are partial differential equations, and they only have one non-dimensional parameter in them, that is a Prandtl number. Because we assume that buoyancy effects are negligible, the Rayleigh number or the Grashof number dropped out of our analysis. Now the standard way of basically proceeding further is to assume a normal mode form of these solutions, of these variables. For students who may not be familiar with it, please consult the lecture on the Introduction to Stability Analysis that I had done a few weeks ago. So we'll start with the normal mode form of these variables. Now we can start by writing down theta hat, which is a function of x, y, z and t, essentially becomes some unknown function h of z e power I alpha xx alpha yy plus sigma t, and w hat plus sigma t. Alpha x and alpha y, these are non-dimensional wave numbers. Remember that, recall that dimensional wave numbers will have units of 1 by length. So these are non-dimensional wave numbers corresponding to x and y directions. I can assume a Fourier decomposition in x and y because these are infinitely far away. There are no boundaries in the x and y direction, and sigma is the complex growth rate, or you can even say complex frequency, such that if real part of sigma is greater than 0, then we have an unstable flow. If the real part of sigma is less than 0, we have a stable flow. And then if real part of sigma is equal to 0, then we have a neutral or marginal stability situation. Okay. Now we want to substitute these normal mode form, which we label them. We'll call this equation number 14. We want to substitute equation 14, the normal mode form, into equations 12 and 13. So before we do this direct substitution, let's evaluate a few terms in, let's say, equation 12. So we have a term like del by del t of theta hat. this term essentially becomes del by del t of h of z e power I alpha xx alpha yy plus sigma t, and this simply becomes sigma h of z. The only term which can be differentiated with time is the last term, e power sigma t, and e power sigma t is just nothing but sigma times e power sigma t. That's exactly what we have, alpha xx plus alpha yy plus sigma t. Similarly, we have another term which is del square of sigma hat. Del square of sigma hat essentially becomes del square by del x square of theta hat, del square by del y square of theta hat, plus del square by del z square of theta hat. Now, del square by del x square essentially gives us I alpha x whole square, and del square by del y square becomes I alpha y whole square. Common to both of them is h of z e power I alpha xx alpha yy plus sigma t. And finally, we have del square by del z square of theta. The only term in theta which is a function of z is h of z. So we have d square h by dz square of e power I alpha xx plus alpha yy plus sigma t. If we take the exponential terms common, then we have d square h by dz square minus alpha x square plus alpha y square of h into the exponential term. Sigma t. Okay. Now we can always define alpha to be square root of alpha x square plus alpha y square, and we will also use one more shorthand notation. We will also say d is nothing but d by dz. So now what we have, if we do the shorthand notation, we have d square of theta hat simply becomes d square minus alpha square of h multiplied by e power I alpha xx alpha yy plus sigma t. This is my d square of theta hat. So now if we substitute, now that we have evaluated del square of theta hat, we have also evaluated the time derivative of theta. We can substitute these into the equation 12, and what we now have is, we have Prandtl number times sigma minus d square minus alpha square, this whole thing times h essentially becomes minus w hat on the right hand side, that is minus f. Note that I am not writing the exponential terms because the w hat also has the same exponential term. So this exponential of I times alpha xx plus alpha yy plus sigma t will cancel out. So this equation 12 essentially becomes this ordinary differential equation. It's an ordinary differential equation because we only have the only derivative that we have in this equation is d by dz, that is capital D. This capital D. Now similarly, equation 13 becomes, remember equation 13 has del by del t, that minus del square, that is sigma minus d square minus alpha square So let me just write this for your benefit. This is my equation 13. So del square essentially becomes d square minus alpha square, right? So therefore now we have sigma minus d square minus alpha square multiplied by another d square minus alpha square of f is equal to 0. Now we can write this is another equation. We can give these equations labels. Let's call this as equation 15a and 15b. So we have two equations. Equation 15 has two parts, a and b. So a is coming from the temperature equation and equation 15b is coming from the the perturbation velocity equation. Now we have to we'll proceed further with the way that Pearson did. So what's the goal of the lecture, or what's the goal of this analysis? One of the goals is to determine, there could be several goals for a stability like this, but one of the key goals is to determine a stability boundary like this. Let me show the stability boundary with a different color. Let's say stability boundary like this. The stability boundary, what does it say? It says that on one side we are stable, on the other side we could be unstable, and if you are on the boundary then we will have neutral stability. So neutral stability here. So recall that unstable means the real part of sigma is greater than 0, and stable means the real part of sigma is less than 0. This is stable. And neutral stability means that a real part of sigma is equal to 0. Now let's understand, I have specifically not shown the axis. I have not said what are these axes, x and y axis, in the stability chart. So but the goal is to get some kind of a stability chart like this. Okay, now the reason I have not specified the axis is because we need to do some more analysis to determine what would be the most appropriate axis to use for this stability chart. Now let's but what does a typical stability chart like this tells us? It will tell us that what is the critical, if I know the value of the x, now the value of x could be something like the wave number. Now if I know a wave of a certain wavelength or the wave number, then the question is, will that, what should be the typical control parameter that is shown on the y-axis, beyond which we will get an unstable solution. Okay, that's the kind of question that we'll be able to answer if we know a stability chart like this. Now let's also understand what are the possible ways in which a flow can be become unstable. Now let's say we have a control parameter, some arbitrary control parameter, which and everything else is being held constant. There's one single control parameter which is which the user, you as a user, have control in varying it, and to then examine what is happening to the stability of the system. Now if you're on one side of the stability boundary, let's say over here, this is in the stable region, you could have two possibilities. You could have a damped solution, purely damped non-oscillatory solution, or you can have a damped oscillatory solution. If you are in the unstable region, on the other hand, you could have a growing, an exponentially growing mode, which is unstable, and this mode, while it's growing, could also be an oscillatory mode. It could be oscillating and growing. Okay, but there is but in the Rayleigh-Benard problem, one of the things that can be shown rigorously is that at the marginal or the neutral boundary, there is the so-called principle of exchange of instabilities is valid. Okay, so this has also been shown by Vidal and Akrivos in 1966, I believe. So if the principle of exchanges is valid, if the principle of exchange of stability is assumed valid, then sigma is equal to 0 on the neutral curve. What does it mean? It means that on this neutral curve means the solution is not growing or decaying, correct? But at the same time, that's not enough to just say that the principle of exchange of stability is valid. When the principle of exchange of stability is said to be valid, then one is also saying that there are no oscillatory modes on this neutral boundary. This excludes, so the principle of exchange of stability excludes oscillatory modes on the neutral curve. So it just says that on one side of the neutral curve you have stable, that is damped solutions. On the other side of the neutral curve you have unstable solutions. But on the neutral curve you actually have a solution which is neither growing or decaying, and it's also non-oscillating. Okay, that's very important. These are non-oscillatory solutions. So sigma, which means that both its real part and imaginary part are identically 0. This can be more easily shown for the Rayleigh-Benard problem, and the strategy for doing this for the Rayleigh-Benard analysis is take these equations and then you can integrate these equations from 0 to 1, okay, and then show that on the neutral boundary, if you are on the neutral boundary, the imaginary part is identically 0. If you are on the neutral boundary, if the real part is 0, then it also shows that you can show that the imaginary part is also identically 0. This such an analysis is much harder for the Marangoni instability. It has been shown in the work of Vidal and Akrivos in 1966, but I will not be able to go through the derivation of this proof of exchange of instability. We will assume that the principle of exchange of stability is valid, which means that sigma is 0. If sigma is 0, then we have with sigma 0, our equations become d square minus alpha square of h is equal to f. Then we have d square minus alpha square whole square of f is equal to 0. These are the equations that we have. And let's call these equations as equations 16. Now, our next step is to determine the boundary conditions. Let's get the easy ones out. At z is equal to 0, we have the perturbation velocity. All of them are 0. This is no slip and no penetration condition. So if W hat is 0 implies F is 0, and if V hat and U hat and V hat are 0, then it means from continuity we have del W by del Z is also 0, and del W by del Z is nothing but capital T of F is 0, that is dF by dZ is 0. And finally we say that H is equal to 0, at z equal to 0, and this means that we have an isothermal condition. The temperature of the bottom wall is absolutely fixed. There are no perturbations to the temperature on the bottom wall, and that's an isothermal condition because the perturbation of temperature H is 0. So we have the conditions here. Let's again summarize this again. So we have at z is equal to 0, we have f is equal to 0, df is 0, and h is 0. Let's give another label for them. This is 17. Now we will have to derive the conditions at z equal to 1. At z is equal to 1, the easiest one is to start with the normal velocity. Normal velocity is 0. Normal velocity is 0 since the interface is flat. Note that this is just an approximation. This is also done by Pearson. Now one could also have undulations on the free surface, which has also been studied in the Marangoni instability context, but this will involve perturbations to the free surface height, and additionally we'll have additional curvature terms, and the Laplace pressure terms as well will enter the discussion. So we'll keep the analysis simple, and again the idea is to focus only on the Marangoni stress contribution. So normal velocity is 0, and this essentially means w hat is 0, and this translates to f is equal to 0 at z equal to 1. This is the first term. Now we also will have another condition, which is we will assume at z equal to 1, we will assume Newton's law of cooling. Cooling is assumed to be valid. Now Newton's law of cooling has been rigorously shown to be a fairly good approximation for a wide range of conditions. In fact, the original experiments of Newton were recently verified in the year 2020. That's just 2 years ago, in the year 2020, and it was shown by the authors in 2020 that Newton's original experiments are fairly good. Newton's law of cooling himself, Newton himself published this work in an anonymous, published this work anonymously. So the Newton's law of cooling, what does it say? It says that at the interface you have conduction, Q conduction. Q conduction would be something like minus K A dt by dz. This is conduction, and Q convection would be H A T minus T naught. Here A is the surface area, H is called the convective heat transfer coefficient. Okay. Then if thermal equilibrium exists, then Q conduction will be equal to the Q convection. So this is nothing but the heat flux because of conduction will be exactly equal to the heat flux because of convection to the atmosphere above. Now again we are assuming that the atmosphere above is held at a constant temperature T naught, but the temperature of the interface itself can vary in space. So if we write down these two, this form, then we have minus Ka d capital T by dz will be Ha T minus T naught. And naturally the horizontal surface area does not matter. And our next step is to write this in terms of theta. So recall that t hat is nothing but t1 minus theta t1 plus theta t naught. Therefore del t by del z, this is the definition of theta. Theta was t1 minus t hat divided by t1 minus t0. So I can have to calculate del t by del z, and this essentially becomes del theta by del z into t0 minus t1. And also we have t minus t naught essentially becomes maybe just substitute this and see. So what we now have is minus k dt by dz. This all should be dimensional. This should be dimensional. Yeah, dt by dz will be t naught minus t1 del theta by del z hat z tilde. This will be equal to h of t hat, that is t tilde, sorry, t1 minus theta t1 plus theta t naught. This is what we have, minus t naught, right? And the right hand side essentially becomes t1 minus t naught minus of theta times t1 minus t naught, that is h times t1 minus t naught into 1 minus theta. And what we now have is minus h of t naught minus t1 into 1 minus theta, or so let's substitute, let's now put everything together. We can cancel out on the left and right hand side t0 minus t1, we can cancel these two out, and what I have is minus k del theta by del z hat is equal to h times theta minus 1. This, remember, is at z hat is equal to d, and now if I use z is z hat by d, we have minus k by d del theta by del z becomes h of theta minus 1. This is at z is equal to 1. Okay. We also should remember that the theta was a base state value plus a perturbation, and this base state value essentially becomes if I substitute this, where the base state value essentially was z. Okay, this implies that theta bar at z is equal to 1 is simply 1. So if we substitute this perturbation, what do we have now is minus k by d of del by del z of theta bar plus epsilon theta hat is nothing but h of theta minus 1. Theta minus 1 is nothing but theta bar plus epsilon theta hat minus 1. Now this quantity here is 1, this quantity here is 1, and what survives now simply is minus k by d of del by del z of theta hat will be h times theta hat. This is at z is equal to 1, right? And we can also write this as del theta hat by del z with a minus sign will be h d by k of theta hat. This quantity h d by k, essentially we can also call it the Nusselt number nu, which is h d by k. And this Nusselt number, how did we get this Nusselt number? We started by basically equating the heat flux from conduction to heat flux to convection. This Nusselt number tells us it's a ratio of convective heat transfer to conductive heat transfer. Right? So now we have derived an important condition. We have minus del theta by del z is Nusselt number times theta hat, or in normal mode form we have minus d capital H is Nusselt number times h. This is an important result, so we will basically label this. We have equation 18 or maybe 19, I think. 17, this was 18, and now we've derived equation 19. And finally we also have to derive a condition for the velocity at the interface. The reason we need a velocity for the interface is, if you look at the equations, it has 4 derivatives for h and 4 derivatives for f and 2 derivatives for h. It's second order it's a second order equation for h, and you have a fourth order equation. The second equation 16b is a fourth order equation. So for h we have got two conditions. One is at z is equal to 0, h is equal to 0, and the other condition that we've just derived is equation 19, which relates the derivative of h at the interface to the local value of h at that location. We have to evaluate the condition at the free surface for f. So we will take it up in the next lecture, but I will basically lay out the outline for it. So the idea is, we have shear stress condition. The shear stress condition, recall we said n dot tau dot t plus minus n dot tau dot t minus, this is minus t hat dot del s of gamma, right? We had also said that the gas above is passive, so the above terms are identically 0, since mu of the fluid above is 0, right? Further, we have said that the interface is flat. Here z is equal to 1 is flat. It means that the derivatives of h with respect to space, that is del h by del x is 0, del h by del y is also 0. These are basically the derivatives of h with respect to the horizontal coordinates. Okay, and what we want to now do is to evaluate this term n dot tau dot t for this problem, and I would like all of you to try and evaluate this expression for a flat interface. But now remember, it's in 3 dimensions. So now you have 2 shear stresses that you will have to keep in mind, tau xz and tau yz, and try and evaluate these expressions and evaluate these jump conditions in terms of dimensional velocities. I will continue this discussion in the next lecture. Thank you.